So this is problem number 6 from the 2011 AP Calculus AB Form B exam. And this is a non-calculator problem, and the problem setup is basically that we have this function f of x, it's equal to g of x minus cosine of x over 2, and we have this graph of g of x to work with. And then in part A we want to find the value of this definite integral. So if we have g of x minus cosine of x over 2 within this definite integral, since it's an integral of f of x, we can break that up into the difference of two separate integrals, since f is a difference of these two separate functions. So I'm going to try to figure out the integral from negative 2 pi to 4 pi of g of x with respect to x, and also the integral from negative 2 pi to 4 pi of cosine of x over 2 with respect to x. And then I'm going to have to take a difference of the two. The integral on the left is going to be the easier integral to deal with, because as long as you remember that a definite integral corresponds to a signed area, you have the graph of g of x provided. So the integral from negative 2 pi to 4 pi of g of x is just going to correspond to this signed area. And since that area is entirely above the x-axis, all we really have to do is not worry about changing the sign of anything, just find the area of this triangle and we're done. So if you treat this as the base of the triangle across the bottom here, the piece on the x-axis, and then this as the height of the triangle, and use the area of a triangle as 1/2 base times height, you can count that the base is going to be 6 pi units across, and the height is going to be 2 pi units upward. Simplify that, cancel these 2's, multiply your pi's together, and you get 6 pi squared. Now the integral on the right is going to be a little bit tougher to deal with, because you have this inner function here. And whenever you have an inner function within an integral, you're going to want to try to let u equal that inner function. So if you let u equal the inner function, and compute du dx, you get 1/2, and then you want to figure out what to replace dx with, so multiply each side by dx, multiply each side by 2, and this is the expression that you're going to be able to put in place of the dx. I put my 2 out in front of the integral, I put my du in place of the dx, I put x over 2 in place of u. Now I have not changed my limits of integration. These are still x values. So I have my little reminder here telling me that I can't put these numbers in place of u. I'm going to have to put this expression back in place of u before I evaluate my integral. If I wanted to put this x value in place of this x and figure out what u equaled when x was negative 2 pi and when x was 4 pi, I could change these to u values. I'm just going to keep them as x values. I just have to be careful not to accidentally put them in place of u. So I take the antiderivative of cosine of u and I get sine of u. I back substitute, put x over 2 back in place of u. Now I'm ready to put 4 pi and negative 2 pi in place of my x and take a difference. And if you think about the sine of 2 pi, that's actually going to be the same as the sine of 0, and that's going to be 0. And then the sine of negative pi, if you cancel those 2's, ends up also being 0. So all this work in the right-hand column here just to figure out that you're subtracting 0, and your result is just going to be 6 pi squared for the integral. In part B, and this is probably the trickiest part of problem number 6, you are asked to find all of the critical points of f between negative 2 pi and 4 pi. So a critical point is going to be any point where your derivative is undefined or any point where your derivative is equal to 0. So before we can do either of those things, we need to find our derivative. So taking the derivative of g of x is going to give us g prime of x, and then taking the derivative of this using the chain rule is going to give us minus negative sine of x over 2 times 1/2 would be the derivative of this inner function right here. Simplifying that a little bit, you can get it to look like this. I want to figure out when my derivative is equal to 0. Now this is going to be a little bit tricky to do because we don't know what g prime of x is right now. But if you think about it, it's not very difficult to figure out, because if you look at the graph of g is just 2 line segments. And so g prime is going to be equal to whatever the slope of this line segment is to the left of 0, and it's going to be equal to whatever the slope of this line segment is to the right of 0. So you see what I have going on up here is I have, to get from this point to this point, a rise of 2 pi and a run of 2 pi. So the slope of this line segment is 2 pi over 2 pi, or 1, and then the slope of this line segment, well, I have a rise of negative 2 pi and a run of 4 pi, right? I go down 2 pi, I go over 4 pi. So my rise is negative 2 pi, my run is 4 pi, reduce that, you get negative 1/2. So To the left of 0, the value of g prime is 1. So I put that in place of g prime. To the right of 0, the value of g prime is negative 1/2. I put that in place of g prime. I just had to keep my two halves separate from each other because g prime isn't equal to 1 or equal to negative 1/2 on the entire interval. It's only equal to those values for these restrictions. So I tried to solve this first, and I moved my 1 across. I multiplied by 2. I looked at this and I realized I can't have the sine of some angle be negative 2. Sine of an angle has to be between negative 1 and 1, so I don't get anything from this. I had to consider it, but I don't get anything. Over here, if you are trying to solve this, add the 1/2, multiply by 2. Now the inverse sine of 1 is going to equal x over 2. And if you think about the inverse sine of 1, you're basically trying to find what angles leave you at this point on the unit circle. Because on the unit circle, your y-coordinate determines sine of whatever angle you're at. So if I want to know when sine of an angle is equal to 1, I need to know what angles are going to leave me right here. Well, the first angle would be pi by 2. If I go around the circle again, I get to 5 pi by 2. If I go around again, I get to 9 pi by 2, and so on. Well, I'm looking at these angles ending up inside the sine function here and making this statement true. But I want to really know what x equals. So if x over 2 equals any of these angles, if I multiply everything on the left side of this equal sign by 2, basically my over 2's are just going to cancel in each and every case. So I'd end up with pi. I'd end up with 5 pi. I would end up with negative 3 pi. There's one over here that we haven't really shown. The only one that I really need to worry about is pi, because 5 pi, negative 3 pi, they would be outside of the domain we were asked to consider here. So we definitely do have a point where the derivative is 0 at x equals pi. But we also have another critical number, because on the graph of g, you have the slope change instantly from 1 to negative 1/2. Because that's a cusp, the slope of the tangent line to the graph of g is undefined at x equals 0. And since f prime depends on g prime, I know that f prime is going to be undefined wherever g prime is undefined, and that happens at this cusp that has an x value of 0. So I have these two values that are going to be critical numbers. X equals pi, it makes the derivative 0. X equals 0 makes the derivative undefined. In part C, we want to take this new function h of x and find h prime of negative pi by 3. Before we can find h prime of negative pi by 3, we need to have h prime of x. So we've taken derivatives of functions that look like this many times over the course of the year, and every single time we've done it, we've used a part of the fundamental theorem of calculus, which says take the upper limit of integration, put it in place of your variable within the integrand, and that's going to be your derivative. But you notice I have this times 3 here. And the reason why I have this times 3 is because the second part of the fundamental theorem of calculus only allows us to handle this type of function's derivative when this is an x. We have an inner function of x right here. So not only do we use the second part of the fundamental theorem and put this in this limit of integration in place of the t, but we also have to finish the chain rule, multiply by the derivative of the limit of integration, the inner function, which is 3. And then if you're evaluating this at negative pi by 3, you put the negative pi by 3 there, cancel your 3's, so you just have a negative pi within the function g. You're going to multiply that by 3. And then if you were trying to figure out what g of negative pi was, well, negative pi on your graph of g would be right here. And if you think about this, it had a slope of 1, this line segment did, from part B. So if I do a rise of 1 and a run of 1, that'll leave me at negative pi comma pi on my graph.